Let's start. So here's a summary. So, so we talked about the line integral of a vector field. So when you talk about the line integral, we should talk about the orientation of a curve. And given that orientation, we can parameterize our curve in CT. For example, C is a function from interval to the space. 하울링이 들리는데? 혹시 하울링 들리나요? 괜찮아요? 어디선가 내 목소리가 들리는 것 같은데? Okay. So, given that parameterization, I can compute this line integral by taking a point CT as a point to evaluate the vector field, and then 어디서 내 목소리가 들리거든요. 혹시 뭐 켜놨어요? 중? 아니죠. 이상하다. And then the inner product with C prime t dt. So basically, this ds vector is 안 들려요? 내 목소리? 아니 뭔가 카메라 스피커 소리가 들리는데? 안 들리세요? 이상하다. 오케이. 네, 다 들리는데. 아니 꺼져 있거든요. 다 꺼져 있어서 이상하다. 네. 여기서 들리는데? 잠깐만, 여기서 안 꺼져 있었네. 네, 이제 괜찮아요. Okay, so this is how we compute. So this ds vector is written basically in terms of C prime t dt. That makes sense because C prime t gives you the direction and the speed, but that speed is normalized by the amount of time passed in a short the dt time passed, which is written here, so that it's scaled into very small amount. So we're taking this inner product to get a scalar function in terms of one variable t. So basically, we are taking a single variable integration. And we also talked about the surface integral of a vector field, and we write that as a f ds vector. So this s is a capital S, this is a small s. And when we talk about this vector field, like surface integral of a vector field, this is a flux. So basically, we measure how much of the vector field is passing passing out across this surface in a normal direction. So basically, we need an orientation of a surface, which means that we need to know in which direction we want to compute our flux. And once we know that direction, we're going to call that as n. So n gives you, let's say that's given a three-dimensional vector. So gives you a three-dimensional vector, which is a unit vector, at every point on the surface, which gives you the normal or orthogonal direction to the surface. So this is our n, and we said that this is also called the orientation of a surface. So given that, what we're going to compute is the double integration of this scalar field, a scalar number. So basically we're taking inner product with f and n. So basically it will be a function of s. So it's a function defined on s. And we're going to integrate that on s. Okay. So look at this f. So f is defined on a space which contains the surface. What we are actually doing is we're only interested in the vector field at the surface. Okay. So we can consider our f to be a vector field defined on the surface S. So when we take the inner product between two vector fields, one is the given vector field and the other is the orientation, they are both defined on S. So basically this inner product gives you a scalar function defined on the set of surface S to the vector times vector inner product vector is a real number. So this is just a function. So once you have a function defined on the surface, you can define an integration over that surface. So that's how you compute. Of course, when you have an parametrization of S, for example, this S is mapping R2 to R3, given that UV is your parameter and XUV, YUV, ZUV is the coordinate function for the point on the surface S. Then you have to choose in which cross product gives you the normal direction of S in this orientation. Suppose that you can have this as an orientation, or SV cross SU could be your orientation. So depending on how you define your orientation, this N is either this or this. So you can plug in this formation and, well, let's see. Let me choose my domain to be D. So D is the domain in the two-dimensional space in UV coordinate, which corresponds in one-to-one correspondence with the surface S in R3 space. So when we rewrite this surface integral, according to what we have discussed a long time ago, is that it's basically integration over this the domain D. And we're going to evaluate this function at the surface, but that point on the surface xyz will be written in terms of uvz. So I'm going to composite these two vector fields with the function s, which parameterize the surface. So f suv their product, and let's see. So again, let me simply choose that this, supposing that this is our orientation, then I'm going to put this into N. So SU, SV, SU, SV. And again, when you integrate a surface integral, then ds component becomes SU, SV cross product in norm times du dv, because you have to modify your small area of S in terms of small area in du dv space. So what we get is you cancel out these, and basically you simply compute these two variable function and these two variable function, and then take the inner product and you integrate whatever that is in terms of uv over d. So that's your flux. So what we're going to talk about today is try to think about what do we get when we get the line integral and the flux over a closed curve on the two-dimensional space, two-dimensional plane. So here's the situation. So the most simplest curve that I can think of is either circle or the square, but I'm going to take the square because it's more easy to take the integral. So let me take a square here. And this square lies in xy space. So I'm going to say the width is delta x and height is delta y. And let's say my starting point is here. So I'm going to call this x0, y0. And my path is counterclockwise direction. So this is our C. So the question is, what do we get for, so again, my vector field is defined on, let's say, some domain, two-dimensional domain that contains this entire curve, which includes the inside of the curve. So let's say I'm going to give an arbitrarily large domain D in two-dimensional space. So this will be my domain for the vector field F. So F is a map from the set of two-dimensional point to the vector field, two-dimensional vector field. Okay. So the question is, what do we get for the line integral of F over the surface, over this curve C? Then let's try to think about the flux over the curve. So here we talked about the flux over the surface, but we can also think about the flux over the curve, simply meaning that we want to measure how much vector field is flowing outward to the surface, outward to the closed curve C. So another question is, what do we get for this? So you have a difference between these two. So we are taking a line integration over C. That means we're going to take a work done over the across along this curve C. So we're going to add small work done along the curve, okay, in direction of this movement. And the second integral means that we're going to add all the vector field flowing outside of this curve C in a perpendicular direction, where n is given as n is the perpendicular normal vector perpendicular to the curve C. Okay, so at every point. So for example, if you pick a point up here, then normal direction is either upward or downward. Or if you pick a point on the left bar, then the normal direction is either left or right. But we're going to pick in a consistent way, so that if I picked the upper direction as my normal direction on this point, then if I move this direction continuously, then I will make my normal direction to be a leftward direction on the left-hand side of this curve. And there's a sharp edge, a sharp corner here, but I cannot find any legitimate normal direction here, but that's okay, because I can just simply omit one point out of this integration interval, and that doesn't change in the value of integration. So I'm not going to define a normal direction at these four corners. Simply there's no normal direction, and I'm not going to take that point into the integration domain. But as we said a long time ago, omitting one point one or finite many points on the integration domain doesn't change your integration. Okay, so here's our two questions. Let's think about the first one. So let's say, let me make a label here. So this is C1 curve, C2 curve, C3, and C4, okay? So when I talk about the integration of the vector field along C, I can split that into 4 line integration, right? And let's try to parameterize each of these curves. So C1t can be parameterized by x0, t delta x, y0, right? So how about C2? C2 can be x0 plus delta x, y0 plus t delta y, right? How about C3? C3 is x0, 1 minus t delta t, and y0 plus delta y. And C4 is x0, y0, 1 minus t, delta y, sorry, delta x, sorry, delta y here. Okay, so these are 4 parameterization of boundaries. And let's try to plug in that into the line integration. So for example, if I plug C1 into the line integration, I'm going to give a coordinate function for our vector field. So for example, let's say if I have x, y on domain D, then the vector, the first coordinate of the vector is given by function pxy, and second coordinate function is qxy. So that's my coordinate functions. So I'm going to plug this parameterization into x and y of this p first. So x0 plus delta t delta x and y0, and q x0 delta x y0. That's my f. And what do I take in a product with? I take c prime t here. I take c prime t and then dt. I take, so what's the c prime t? So here's the c1 prime t. That's delta x 0, right? So delta x 0 dt. Okay. So, and then let's try to think about c2. And then what's the domain of integration? 0 to 1, yes. And how about C2? So still it's from 0 to 1. And I will say I have to plug this one. So we have P. Well, let's make it simpler. So whatever I do when I plug in these coordinates to F, I have to take in a product with C prime t. So when I take the C prime t, only the second part survives as delta y. So I don't need P in the second integration. So I'm going to plug Q x0 delta x, y0 t delta y times delta y dt. Okay? So that's our C2 integration. Well, I can simplify this part too. If I do this, I get only delta x dt, right? So how about C3? C3, I'm going to omit the convention notation there, is 0 to 1 of what? This survives, okay, right? So P x0, 1 minus t delta x times what? If you take the c prime t, minus delta x, right? Minus delta x dt. And how about c4? This is 0, 1, q, oh, sorry, I forgot to put one more coordinates here. So, comma, y0 plus delta y minus delta x dt. And here we put x0, y0, 1 minus t delta y and minus delta y dt, right? Let's combine all of these integrations. So I'm going to combine the left-hand side, which gives the combination of right-hand side. So let's combine upper two to get p x0 plus t delta x y0 minus p x0 1 minus t delta x y0 delta y, okay, and delta x dt, right? And well, before we put dt, and what? We have q x0 plus delta x, y0 plus t delta y minus q x0 y0 plus 1 minus t delta y, and let's see, I had a parenthesis here, so delta y and dt, right? Let's try to simplify. What do I get here? So when t is from 0 to 1, I'm moving my okay, so I have to make one more argument here before I talk about this. Right. So then that is equals to 0 to 1 of so there's no way to simplify these long descriptions, so I can only write everything down here. So let's take out P0, Y0 here, and then add P0, Y0 again. So that's going to be combined to x0, 1 minus t delta x, y0 plus delta y minus x0, y0, and then delta x dt. Okay, and then I'm going to do the similar to the second part. So I'm going to subtract q. Q x0 delta x, y0 t delta y minus q x0 y0, and maybe here's delta x. and then qx0 y0 plus 1 minus t delta y minus q x0 y0. So there's a minus plus here, so canceling out happens. Delta y dt. Okay, let's think about this part. What are we doing here? So we are subtracting a value of function f at these 2 points, right? Right? So look at this f0 plus delta t delta x comma y. So not that point, sorry. So maybe somewhere in middle here. So this is t delta x because t is from 0 to 1, right? And more precisely, this length is t delta x, right? So when you subtract these two, we're talking about the difference of value of p in when I change the value of x only. I fixed y here, okay? I fixed y. So I can approximate these value, or actually there is a theorem, mean value theorem, that this value is equal to partial derivative of x at somewhere between 0 and 1 of this. So this is equals to some value of partial derivative times, because we only look at the difference between a value of functions. So if you want to approximate that with the partial derivative, then we have to modify that with delta x. There comes the what comes in here. So we have t. So it's not delta t. This, by the way, this is delta x. So ratio between the difference of y and x is almost equals to the value in between these two intervals. So I have to take the difference between these two values. So it's going to be t delta x. Okay. So what I'm doing here is I'm simply choosing a point, some point in between these two points, so that partial derivative at this point is equal to, which is partial derivative, which gives the instant rate of change, is equal to the average rate of change of function p at the left-hand point and the right point here somewhere. Okay, so that's a mean value theorem. So mean value theorem for single variable function. And let's look at this part. Okay. So I cannot use the mean value theorem right away here because I'm not fixing y. It's the same value here, but there's a way to modify your mean value theorem in two-dimensional or two-variable function. So I'm not going to make a detailed argument, but let's assume that delta y is very small. So it's almost equals to y0. So I can approximate this difference between the value of p as a value of p on fixed y, but different x. Okay, so this is also equals to right? So I'm doing correct. correct way, right? Did I miss something? Yes?
I feel like the partial derivative of del f and del x, and I think the parameter should be x0 and y0.
x0, y0? Which one?
T delta x means the change value.
Yes.
So I think.
So only x is changing, right?
Yes.
So we're changing the difference of, we're looking at the difference of f in terms of x. So this average difference, average rate of change is equal to the instant rate of change at some point in between x0 and x0 plus t delta x.
맞는데
네.
x에 대한 편미분 함수인가요? 편미분인가요? 결국 그 편미분이 x0, y0에서 행해지는 거니까 x0 플러스 t 델타 x가 아니라 x0가 되는 거예요. 저기 그때 편미분은.
No, I mean, so what I'm doing here, this identity, is that I'm fixing y. So you can think this p as a function of one variable function. So if you have one variable function, and let's say we are at x0, and here is x0 plus t delta x. We want to think about the difference between 2 points, value of 2 points, over this interval t delta x. So the average rate of change is px plus t delta x minus px0 divided by t delta x. Okay, but there is a point whose instant rate of change is equal to the slope. So that's going to be my x0 plus t0 delta x. So this is equals to px. So that's the derivative in terms of x of x0 t0 delta x. So that's where it comes from. Okay. I think it's right, but all right. Well, let's finish it, but and then see what's going on at the end. So here, I'm not having the same y, but I can approximately say that this is equals to the partial derivative of p at some point in between x0 and x0 t delta x, and I'm looking at the difference between these two. So I can say that this is equal to some point. Let's say I can replace this entire point to be x0 star, something like that, right? Instead of using t0, I'm trying to make it into this whole thing as x0 star, okay? So meaning that x0 is some point in between these two numbers, okay? And I do the same thing. So I'm going to take x0 star, meaning that it's not always the same point, but it's going to be almost equals to these point times. In this case, now, if you're looking at the no, it doesn't matter, right? So you're just looking at these two, right? So the interval of domain is this thing. So we have 1 minus, sorry, I forgot t delta x, okay? 1 minus t delta x, okay? So this part is almost equals to that part. Okay. 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 I have to think a little bit. Let me give me 1 minute to think about whether I have to think carefully. I'm going in the right track. So I'm doing a line integration. Okay, so I'm doing a line integration, and I'm looking at these two line integration. Okay. All right. And then so I was looking at this one, right? I was looking at difference of these two. Okay. So I was trying to give and subtract and add the same thing to make this part into different setup. Actually, that's not what I want. I mean, I think I didn't have to do this part. So let's think about this differently. So here, so what we're doing here is okay. So what we're doing here, when we're looking at this part, okay, is that I'm moving this direction, and at the same time I'm moving this direction, okay? So it seems like I'm subtracting a value of p in a diagonal direction. So if I had point here, then on C3 point of view, I'm looking at this point. And if I'm looking at this point, then I'm looking at this point, and then it's going in the opposite direction. But I'm going to make a different observation about that. So maybe, sorry, but I forget about what I've said here. So I really didn't need this. So let's try to rewrite this second part of P, okay? So the C3 part can be written as 0 to 1 of P. So I'm going to replace this 1 minus t into u, okay? So then when t is from 0 to 1, u is from 1 to 0, and this is going to be minus of p x0 u delta x, comma y0 plus delta y, right? And then we have delta x. And at the end we had the dt, but dt is equals to d minus du. So we have two minuses, and I want to interchange these limits. Then I have another minus. So basically I have minus of, let me write in the second line. So we have minus of 0 to 1 of p x0 u delta x y0 plus delta y delta x du, right? Okay. Now, u is nothing. U doesn't have meaning. U itself is just the intermediate symbol to compute the integration. So I can replace my u in terms of t, okay? Here, okay? So, and then let's combine that with integration on C1. So C1 plus C3 now becomes, C1 is already written in terms of t from 0 to 1. So it's from 0 to 1 of p of x0 t delta x y0 minus, and p, so I'm going to put my minus inside the integration and then combine that here. So x0 t delta x y0 delta y, okay? The same thing here, and then delta x dt, okay? And well, let's, for simplicity, interchange this subtraction and then put the minus outside. So minus 0 to 1 of p x0 t delta x and y0 plus delta y minus p x0 t delta x y0 delta x dt. Okay? Now let's use the mean value theorem. Okay? So it's not that mean value theorem is not used at all, but it's used in a different context. So the idea is exactly the same I just mentioned before, but here we have fixed x. X is same, okay? Y is changed, okay? We are looking at the difference between p at y0 and y0 plus delta x. So this is equal, actually equal to the partial derivative of p by y at fixed x and some point between y0 and y plus delta y. So I'm going to call that as y1 here, okay? And then multiply that with these delta y, because we are looking at the difference between y and y delta y, the delta y, okay? So by the way, the delta y, y1 is some point in between y0 plus delta y and y0. Okay. And let's finish our calculation. So this is becoming 0, 1 of delta p delta y x0 t delta x y1. So here's delta x and here's delta y and dt, right? Where did we have delta x here? Right. We had delta x right there. And, okay, so okay, so this is as far as we can go. And I had to make a bold assumption again that there is a reason why I put my width and height as delta x and delta y. I'm going to make this as small as possible, infinitesimally small. Okay. So that will give me let's see, approximately these number, the delta p over delta y, is approximately equal across any point over this from x0 to x0 plus delta x. So this is simply an assumption, okay? Assume that delta x and delta y are very, very small. So when you talk about the small number, we usually use this symbol that it's very small and it's very far away from 1. Okay. Writing again, very small. Then this delta p, delta y is almost a constant over this domain, over the curve, or over the curve and inside the curve. Okay, so assuming there's almost no change when I move my point here to here, when I compute py, we say that there's no change. So then what? Then this is almost equals to minus integration from 0, 1 to delta p, delta y at any point inside of this curve C. So I'm going to pick a random point or a fixed point, x0, y0, because it's almost equal. And then delta x, delta y dt. So this is constant. Delta x, delta y's are constant. So I'm simply taking integration of 1 over 0, 1. So this is 1 is equals to minus dp dy of x0, y0, delta x, delta y. Okay? That's when we add this C1 and C2 together. Okay? So let's add C2 and C4 together and see what's going on. Yes.
I have a question. Why did you use Y1?
Why do I use Y1? Because I picked some random Y1, or there's some Y1 in between Y0 and Y0 plus delta Y that satisfies that this difference is equals to the partial derivative times the difference of Y.
Why are you using the random Y1?
That's the mean value theorem, just I mentioned before. But that doesn't really matter because I'm going to assume that this point, the value of partial derivative is almost constant. So I can pick any point here. Okay? But in really, this equation, this equality is real. There is a point y1 that satisfies this equality. Okay? It's not just approximation. It's a mean value theorem. Okay? Because we have fixed x, only changing y. So we can think of this as a one variable function. And this gives the approximate difference between, this gives the, if I divided that by delta y, it gives the average rate of change. And that average rate of change is the same as instant rate of change at some point between interval. Okay. All right. So and then what's next? So we have to add C2 and C4. So look at this, C2 and C4. So so what we're going to do, we are going to do the same thing. So let's replace 1 minus t here as u again, okay? So that's going to be, so let's write the C2 again, the C2 first. It's Q x0 delta x, y0 delta y. And this part, now let's see. I replace this as u. That's going to be this constant, okay? And that's going to be minus delta u. And my limit will be changed to 1 to 0. So if I switch back to 0 to 1, I have minus. So how many minus we have? So 1 minus from here, 1 was already here, and minus 1 appears at the end. So we have 3 minuses. Basically, you have 1 minus. So and then I replace my u back to t. So I get minus here. Q x0 delta x, and sorry, x, just x here, just x, and y0 for t, so t delta y dt, right? So here I forgot to put t here. T delta y, okay? So in this case, y is fixed, okay? Y is fixed, so we can think this function as, this situation as just function of x. So the same mean value theorem tells you that this is equal, not approximately equal, just mean value theorem, says that this is equal to delta q delta x, x1 in this case. So x1 is something, some point in between x0 and x0 plus delta x, comma y0 plus t delta x. Right? So that means we have 0 to 1 of delta q, delta x, x1, y0 plus t delta y. Oh, sorry, I forgot the important part. So we have difference of x0 delta plus x and x0, so we should multiply that by the distance of x. So we have, forgot delta y here again, right? So we have delta y dt. So here's delta y, here's delta x. We have delta x, delta y dt. And again, we assume the same thing, that delta x, delta y are very small, so we have no difference in between any point, a point value of p and q at any point. Assume the same thing, assumption, says that I can replace this as just a constant value, say that this is evaluated at x0 and y0. So equals to del q, del y, x0, y0, del x, del y, dt. So then we're just integrating a constant. So this is equals to delta q, delta y, x0, y0, delta x, delta y. Okay? So what I'm trying to say is let's try to combine everything. Okay? So what we have done is integration over the curve of this vector field, and at the end it's approximately equal to sum of these two numbers, right? This one and that one. So that these two contains delta and delta y, and white. This is x. Y, it becomes y. So this is x. Okay. This is x, and dp dy delta x delta y. Okay. So here's an assumption. Delta x and delta y are very small, and our partial derivative is approximately evaluated at point x0, y0, which is any one point in this circle, in this curve C. And that only happens for very small curve with rectangular shape. But since we know that this holds for very small curve, what we can do is that when you have a large curve, I can approximately say that suppose that I have a curve like this. I'm going to subdivide that curve into regular pieces, something like, okay, like pieces like this, okay, and then suppose that these are very small pieces. I'm going to make an same argument for every piece of this circle, a piece of this curve. Okay. So I'm going to take a line integration on these small piece of curve, and then when I do the line integration over this curve, it's approximately equal to taking these value here. Okay. So let's say I have Cij here. So integration over Cij of f ds is approximately equal to dq minus dp. So that is evaluated at any point. I'm going to call it xi, yj here. Okay, so any point inside of this curve. Okay, and then multiply that with delta y, delta x. So delta y is the height of this curve, and delta x is width of this curve. Okay. So I'm going to do this for every curve that's enclosed by this curve, and I'm going to add them all on the left and right side. So if I do the integration, think about the situation at the boundary. So let's say I have this curve, and I have these inner curve. Okay. So look at this side. So we already had a line integration on this direction, and this line integral cancels out with the line integration on the upper curve, which goes from opposite direction on the side that on the shared side. Okay, so this cancels out. Line integration of inside lines all disappears. So what survives is the line integration on the boundaries. Okay? So in other words, if you want to find out the line integration over the boundary curve, so this curve is the C, okay, is equals to the sum of all line integration of inside curves. And we know that this is equal to this thing. So we have sum of dq dx dp dy of xi yj and delta xi delta yj, right? So xi yj is any point inside of this each curve here, and this is just a function which evaluated that point on each of this region bounded by the circle C, and there is the delta xy delta yj, which becomes dx dy when you reinterpret this summation as a double integration. So what it becomes, this is equal to, let's call the domain that contained in the C as D. So this becomes the integration over D of qx minus py dx dy. So where we started from? We started from line integration, and we ended up getting a double integration. So the difference is that we had a line integration over the curve, which is one-dimensional thing, but it's same thing as a double integration over two-dimensional domain. And this curve was moving counterclockwise, okay? So that's how we get this part. If C were going in the clockwise direction, all the computation we had should have -1 outside, okay? So we have a minus of this term. So let me summarize. Let C be a curve on R2, closed curve. So closed means we have a starting point same as end point, which encloses the domain D, okay? Let the F be a vector field defined on this D, so entire D, okay? Be a vector field such that this fxy is p comma q and pq. So the crucial point that we had in this argument is that pq satisfies the mean value theorem. So in order to apply the mean value theorem to any function, you should have a function whose derivative is continuous. So that's usually called a C1 condition. So that's what I'm going to say. Continuously differentiable which means all partial derivatives are continuous. So you don't really have to dig into what's the meaning and what's going on with this condition, because everything that we're going to take as an exercise will be a continuous differentiable function. Like polynomial exponential functions and sine and cosine functions are all continuous differentiable functions. So you don't have to worry about that. Have a function. Worry about the situation that does not satisfy this condition. Then the line integration over this curve is equals to the double integration of qx minus py, assuming that this c is counterclockwise direction. Okay. Sometimes when you have a line integration over closed surface, the symbol for line integration is used as this circle integration. Okay, so meaning that this circle is line integration over closed curve. Okay, meaning that it's a closed line integration over closed curve. So this is abbreviation of the argument that we made, and there's a big name for this. This is called Green's theorem. And here's a name for this also. So because we can't provide every time what PQ are, so we can abbreviate this QX minus PY as rotation of F. Okay, this is R. Okay. Rot of F. I didn't use curl yet, so because curl is only for three-dimensional vector field. We have a two-dimensional vector field, and if you get a rotation of F for two-dimensional vector field, then you get a scalar function qx minus py. Okay, that answers the first one. Any questions? I can give a more concrete proof for the Green theorem, because if you are not comfortable with the vague argument that this is approximately equal to that rot of F, then let me give a proof. So I'm going to give a proof for Grimm's theorem where the curve is convex curve. So meaning that suppose that I have a curve that's on xy space, which can be written as the following way. So this curve is bounded by two graphs. One is y equals to g1x, and the other is y equals to g2x, and x is from A to B. So let's suppose that this is our situation. So our curve is moving thisward, counterclockwise. Okay. Let's try to compute a vector field over this curve. First part is try to find the line integration over lower border of this curve. So I'm going to move my x from A to B, assuming that my f is two-dimensional, whose coordinate functions are PQ, as always we did. So I'm going to plug in the parameterization of this lower part of this curve C. So that's going to be Ct equals to t comma g1x, right? G1t, sorry. So the lower part will be P, Q, inner product with C prime T. Let's say C1 here. So we have C1 prime T. It's 1 comma G1 prime T. Okay. And then next, I'm going to integrate over this part. So that gives x from B to A instead of A to B, and because I'm moving counterclockwise direction. So then I'm going to use my parameterization C to T, which is T comma G2T. And it's going to be PQ time inner product 1 comma G2T dt. Okay? So before I combine these two integrations, I have to switch the limit here, so, and then I have minus sign. So it's going to be A to B of, so first let's look at the first one. So these PQ are evaluated at these points, which follows this T comma G1T. So I'm going to plug that in. So P T G1T 1 times 1, right? And then Q T G1T times G prime T. And then you subtract this, because I switched this A and B. P T G2T plus, actually minus Q T G2T G2 prime T dt. So let's forgot the parenthesis here. Prime T, right? Let's say let's split this two together here. So I'm going to think about this PTG1T minus PTG2T first, and then AB of QT G1T G1 prime T minus QT G2T G2 prime T dt next. Okay? So let's look at the first one. So you have something that subtract each other, and then you plug it, and then the difference is that you plug G1 and G2 on the Y part. Okay? So way you can obtain this is that you can use the fundamental theorem of calculus, okay, assuming that this P already inside of this integrand is fixed x, so only y changes. So assuming that you applied the fundamental theorem of calculus on the function of y, so in order to have that situation is that you are integrating the G2t to G1t of a function which is the derivative of the p, assuming the p is only a single variable function in terms of y. So this is your situation, right? So t, y, dy. So once you think about this part inside of this bracket, you get the integrand here, right? Right? And then you have dt. So although I used t, but I can replace t by x, okay? So let's just rename my t in terms of x. X, okay? So that's the first part. How about the second part? So we have a to b, and now the situation is a little bit different. Instead of have just these two, we had G1 prime t and G2 prime t came out, right? How could we obtain this? So if you think about the first part, this one, Qt G1t G1 prime t, what does it equal to? Right. So it seems like a chain rule, right? Like you have a composite and then try to take a derivative, then you somehow you get this one. So let's say, actually, sorry that I also made a mistake here. So it's hard to make an argument from now on. So I have to make a separate argument for the second part of here. Okay. So let's leave it here. But let's think about the situation. These two situation for these parts in a separate way. So where did it came from? So it came from these Q's, right? These two parts, okay? So I could have obtained this part if I used my vector field as p, 0 instead of p, q. I could have just this as a result. So this is equals to line integration of p0 vector field over the curve S. Okay, and then I'm going to make a very convex shaped ball here. So this is G1, and then I'm going to make another observation that okay, here, and I'm going to rethink about the lower and upper part of this curve in x, h1x and x equals to h2y, h1y here, okay? So it's the same curve, but with a different perspective. And in that perspective, let's look at what 0Q line integration is. So I'm not going to have anything on the x-coordinate parts of the vector field. So then, let's look at this situation, CD here. So still, it's a counterclockwise direction. Okay, so let's look at these left parts again. So I'm moving from D to C of Q of, if I parameterize my H1 as D1, so let's say D1T is now, T is the coordinate function for Y, okay, so T and H1T. I'm plugging that here, H1T, comma T, inner product with D1 prime T, which is so we have we have 0 on the first part, and Q part multiplied with the second part of this D1 prime T. So we only have 1 here, so we have dt here. And then, let me write it again. So if there's someone who's confused about what I'm doing here. So when I plug in this D1 here to compute the line integration, for the left part of the circle, left part of the curve, I get H1T inner product with H1 prime T1 dt, and then dt, and then the right part is parameterized by D2T, H2T, comma T. So T is now from C to D, is C to D of 0Q, H2T, T inner product with H2 prime T, comma 1 dt. Okay, so let's make the limit equal. So it's going to be C to D of what? First we have Q H2T 1 T minus, so we have minus here because we switched C and D. Q, so here we only have Q part survive with 1 here. Q H1T T dt. So we make the similar argument that we did in the P part. So this seems like I apply the fundamental theorem of calculus on dq dx, and then integrate from h1 x to h2x dq dx xy dx y. Okay? So that's the line integration on this vector field. So let's combine these two. P0 over the same curve, we are taking a line integration of P0 and 0Q vector field and add them together. So if I combine these two integration, since we are taking integration over the same curve with the same orientation, I can add these two vector field. Okay, so we get PQ ds, which is simply the integration of original vector field. And if you're looking at the result, what we have gotten here is for the first part, this part is equals to A to B of G1 to G2. So here we had G2 to G1. I'm going to change G1 to G2. Then I have minus come out, Py dy dx. And then C to D of H1 to H2 of Qx dx dy. So let's look at what we are actually doing here for this iterated integral. We are doing a double integration over the domain D. The same domain, because this domain is written in terms of first x from A to B and y from G to G1 to G2, and also can be written as first y from C to D and x from H1 to H2, right? So basically we are talking about the same domain. So this is equals to the double integral of minus Py over D plus Qx over D. So therefore, we have Qx minus Py dx dy over D. So we have a line integration equal to the surface of the double integral. Now this applies, there should be a question. This applies only for this convex domain, which means that the domain that has two ways of description. But you can, if you have a randomly figured curve, and the domain surrounded by that curve, like this one. So if you have this kind of curve, you cannot directly use that proof, but you can subdivide your curve and the domain to make each of subdivision satisfies this condition. For example, let's say you pick maybe somewhere here, yep. I think that's enough. I think that's enough. Let's say you can use the idea of proof for this first part. Okay, so you can say this is C1. Okay, and you can take the second part as C2. Okay, so this C2, and then the last part is C3. Okay. So then there is a side that shares each other. But if you're looking at C1, it's going upward in this side, and C2, you're going downward this side, so it will cancel out. So every line that inside of this big curve, it will cancel out, and then what left over is only the boundary parts. You apply that argument to each of these domains and each of these surrounding curve, then you see these curves are all convex. So you can describe your domain in two different ways. So you can use the same argument. Then you know that the Green theorem holds for these three regions. You can combine them to get the Green theorem for entire curve and the region. Okay? That's how you finish your argument. Now, let's think about the second question. What do we get when we think about the flux? What do we get for this flux? since we know that Green's theorem, the answer is easy. Just let's try to think about this situation. So let's rewrite this. The PQ for F, and we need normal direction, right? So this is our normal direction with as a unit vector, and for each point of curve, there is a tangential direction of this parameterization, and I'm going to write that as x prime t, y prime t, okay? Assuming that my xt is just xt, yt, okay? So in order to have a normal direction as a unit vector, I have to find out the vector that is orthogonal to that. And also I want to have a direction that is counterclockwise, not the counterclockwise, outward direction, sorry. So outward direction. Say, I think I should make an opposite direction, right? Sorry. So this is counterclockwise direction, sorry. So this is how you parameterize your curve. So if you have this vector as x prime comma y prime, in order to have this normal vector, not that direction, not this direction as your normal vector, what's the first coordinate to be? So your normal vector should be 0 when you take the inner product with c prime t, right? So it's either minus y prime t xt or y prime t minus x prime t. It's either this or that, okay? If you want this direction, if the tangential direction is this part, then what? I think you need this, right? I think you need this for this direction. So I'm going to use that as my normal direction. Okay? Because if you're looking at this tangential direction, the x-coordinate is minus, y-coordinate is plus. You want plus plus, right? So this is the only way you get plus plus. And then, since you want the unit vector, you have to normalize it. X prime square, y prime square, okay? So you're going to take an inner product here. So x prime square, y prime square, y prime minus x prime, and ds. Okay? And then let's assume that I parameterized my curve C and try to compute this line integral. So this is equals to some integration from A to B of, so it's P, Q, and inner product minus plus y prime minus x prime, and x prime square, y prime square, and ds term becomes c prime t norm dt, right? So these P and Q are evaluated at C, so CT. So that's going to be PCT times Y prime T, okay? And then what? Q minus Q CT times X prime T. So C prime T norm is equals to the denominator here, so this cancels out. We have only dt left. Now, let's think about this situation again. I'm going to rewrite in terms of x and y instead of t. So what we are doing here is actually the line integration over the closed curve of p, and p is multiplied with y prime t and dt. So that's basically dy. Okay? And here we have q x prime dt. So x prime dt is dx. So we have q dx. So this is equal to basically the line integral of another different vector field whose x coordinate is minus q, y coordinate is p. Okay? So the reason why we had different vector field is not, we are not taking a line integral of f, we are taking a flux over f. So anyway, I change it to line integral of this vector field again. Now let's use Green's theorem. What's the Green's theorem? So in the Green's theorem, this minus q work as a p, and p work as q. So whatever you have to remember is that the y component is partially differentiated by x, and x component is partially differentiated by y, and you add subtract each other. So basically, you're taking a double integration of px minus of minus qy dx dy. So which is px plus qy dx dy. So where we came from is here. We want to find the flux, and it turns out that the flux is equals to the double integration over the enclosed area of this px plus qy. Now we call this px plus qy as divergence of f. Okay? What does it mean that we have non-zero divergence? What does it mean? Suppose that I have small box here, the same situation we just mentioned in the beginning of the class. We have delta x, delta y, and here we have x0 and y0. And since delta x, delta y are so small that we can think this delta px plus qy are almost equal, almost constant. Assume that delta x, delta y are very small, so that this divergence of f is almost constant. On this domain D, okay? All right? So then, what do we get from this flux? Flux. is, by this argument, almost equal to the divergence of f at x0, y0 times what? Since we assume that this is almost equal to constant, we simply take the area of domain D, delta x, delta y. Okay? So this gives lots of interpretation. So you can interpret the flux from this argument, and also you can interpret the divergence from this argument. First of all, the flux can be written as the divergence times the flux across, let's say, flux over very small closed curve is approximately equal to the area of that enclosed region times the divergence at the point inside of this curve. Another way of describing it is flux over the closed curve have some boundary of positive flux and some boundary of negative flux, right? So if you think about the vector field is flowing across this closed curve C over the region D, then there's some boundaries are going outward and some boundaries going inward. So net flow across this border is equal to the area times how much it has expanded inside of this domain D. So the rate of expansion is measured by divergence. Okay? If there were no expansion, exactly the same amount go inward will go outward. Okay? There's no leftover, or there's no increase of volume or increase of this flux. You can also interpret your divergence using this argument, that if you take the one point and compute the divergence, so divergence of vector field is a scalar number. Okay? That number means that how much of flux is going out how much of the flux is changes across the small closed curve surrounding that point. So for example, you have a point on x0 and y0, and take your small enclosed curve around this x0 and y0. There is there is an area of that region, and if you take the divergence of the function vector field f at x0 and y0, this is total flux across the boundary so let me write it more intuitive way. So total flux across the boundary of a region, or actually small region, surrounding the point per unit of area. So it's not an absolute value, so this last part is important. So because we have delta x delta y term appears here. So divergence doesn't give you absolute value of flux around this point x, comma y. So depending on how large your area is, which contains the point, your total flux could be larger and or smaller. So, but divergence gives you how much flux is going out at that point per unit of area. Okay, the per unit of area. Okay, so that kind of gives you idea how this divergence means in a physical sense. Suppose that you have somehow a dispersing particle at this point, or somehow you have a spring of water that's flowing out at this point, and you try to measure how much water is flowing. I mean, so water is not a good way of talking about. So it's not water. Sorry. So maybe. Let's say, let's talk about the particle of air, the particle molecule that floating around in the air, and try to find out how much of that volume of molecule is expanding at this point. So if you try to put a three-dimensional balloon over this point, and then trying to measure how much of this particle is flowing out from this balloon, then if you take a large balloon, then smaller balloon, then the measurement of the total amount of flux is larger in a larger balloon and smaller in the smaller balloon. Okay, but divergence is actually measuring that flux per unit of area or unit of volume. I use the area because my vector field is two-dimensional vector field. If you use the three-dimensional vector field, it's going to be replaced by volume. So we talked about the Green theorem. So let's summarize. And using the Green theorem, we talked about what's the meaning of the flux, how to compute the flux across this closed curve, and what's the meaning about the divergence. Also, we talked about what's the meaning of, we didn't talk about the meaning of rotation, but we're going to talk about how we generalize this situation in three-dimensional vector field. Okay, so think about the situation first. In two-dimensional vector field, we had a closed curve. In three-dimensional vector field, we're going to have a closed surface, which encloses three-dimensional volume. Okay, and think about if we think about the flux, then we need to think about the closed surface to find out the flux. But when you think about the curve line integration, and the line integration is transformed into the double integral. And if you want to try to generalize to three-dimensional vector field, this line, the curve, is not a two-dimensional curve. It's going to be a three-dimensional curve. And this three-dimensional curve is bounding a surface in three-dimensional space. So we're going to talk about how this line integration over three-dimensional curve is transformed into the surface integral over the closed surface bounded by the curve over the three-dimensional vector field. So that's called the Stokes theorem. So next time we're going to talk about the Stokes theorem, and then the divergence theorem, and then we will have one more week to go. So the last week will be about how can we generalize these arguments to higher dimensional space? So as I mentioned in the beginning, maybe if you remember it correctly, the Stokes theorem, Green's theorem, the divergence theorem, the three main theorem that usually appears at the end of the calculus book, any calculus book, is just the same theory. Okay? It's just the same theory. And because we are living in the three-dimensional space, but your work, the research, will not be limited in three-dimensional space. So it's better to know how to generalize to any dimension. So thank you for listening. We are going to have... Okay, so let me announce one more time, although I announced it on the LMS site. Next Friday is the deadline for every assignment. I'm going to close every Notion pages. You're not going to able to edit it anymore. So midnight, December 3rd is the deadline. If you have any question, please ask any time. And if you have any concern, also ask any time, because I'm not asking you to do lots of things. So just do whatever you can do in a conscientious way, okay? So I don't want to make you suffer. All right, so thank you very much and see you on Friday.